All right, so we are live, everyone. My name is Jesse, and I am with Exploring by the Seat of Your Pants. For those joining us for the first time, we are all about bringing conservation, adventure, and science to people around the world. And so, of course, there are no classrooms in right now, so we appreciate all of you for tuning in live on YouTube. We are going to be doing sessions every day, many sessions a day for the next few weeks as schools are out. So we really appreciate you tuning in and hope you can check us out throughout the rest of the day and beyond. So right now it's very exciting. We are joined live in Montreal by Nathalie Ouellette. So she is an astrophysicist and an amazing science communicator. She's done work all over the world to understand space and share it with the public. She's most notable for the fact that she is the coordinator of the Institute of Research of Exoplanets at the University of Montreal and the Canadian Science Communicator for the James Webb Space Telescope, one of the most incredible pieces of machinery that we've ever built, going up sometime in the next 2 years. We're not really sure quite when yet, but I'm not going to steal her thunder. Without further ado, thank you so much for joining us, everyone, and take it away, Nathalie.
Thanks, Jesse. So I'm Nathalie Ouellette, and I am in Montreal, even though my background might imply otherwise. I'm just testing out some new virtual backgrounds as we're all getting familiar with teleworking and virtual online sessions with the current context. But I'm super excited to talk about space and astronomy and the James Webb Space Telescope specifically. So I will be giving a really short presentation, lots of cool information about astronomy, exoplanets, and James Webb. And after that, I'm happy to answer any questions you might have. So I'm going to go ahead and share my screen now. So hopefully you can all see my slides here. And I'll talk a little bit about the work that I do. So I am an astronomer, an astrophysicist, and that implies going to telescopes a lot of the time. It's not as much as it used to be because now a lot of that is automated, and that's especially really handy for instances like now. But I have been lucky enough to go to some telescopes in some pretty exotic locales around the world. Here you have some telescopes that are on Mauna Kea, which is a really tall mountain in Hawaii. And when you think of Hawaii, you think of the beaches, you think of tropical weather and palm trees, but Mauna Kea is actually really, really tall. So you actually get a real legitimate winter there. So you see the little patch of white in front of the foremost telescope there. That's snow that's there. So I have been up to Mauna Kea and we've had sessions that we had to cancel because there were ice storms and everything. So people don't think of ice storms when they think of Hawaii, but it's a really, really tall mountain, which is really handy to do astronomy. So in the foreground, you have the Gemini telescope, which has a big Canadian component. And in the background, the white little telescope, you have the Canadian France Hawaii telescope, or the CFHT. So those are two really great telescopes that I've had the chance to visit. We've also used telescopes a lot of the time in deserts. So this one is a telescope called the Sloan Digital Skies Survey. And this one is really special. It's in New Mexico, very, very dry weather. So there you don't have a lot of clouds, you don't have a lot of water vapor, which is not really good for astronomy. But this one, it doesn't take the projects of specific astronomers and then takes data for those astronomers and gives it to them. It just takes a census or a big survey of the entire sky and gives all of that data publicly to anyone who's interested. So not only astronomers, but even you could go right now on SDSS.org, and you could find all of the data that's been taken by this really world-class telescope and do science yourself. And there's actually some little programs there that you can use to look at your favorite object, your favorite star, your favorite galaxy. So that's really, really handy. So those are some of the telescopes that we use here on the Earth. And that's really handy because you can take your time building them. And if they break down, you can then fix them. But there are a lot of issues with doing astronomy from what we call ground-based telescopes, or the telescopes that I mentioned here. So we have to deal with stuff like light pollution. That's why we build away from cities. We have to try to have really clear skies, so no clouds, very dry air around you, and you have to get really, really high up where the oxygen and the atmosphere is generally really thin, because there's something in astronomy called atmospheric seeing, and that's a fancy name that's basically just means that the atmosphere makes the different objects that you're looking at sort of twinkle. So that's why stars are twinkling when you're looking at them through the atmosphere. The atmosphere is sort of jostling around and jostling the light rays coming from those objects, and you don't like that. But at the same time, it's important when you're an astronomer or an engineer to have the oxygen around you to build it. So it's sort of like an interesting balance that you have to strike. But to try to counteract all those different things, we can instead send telescopes up into space. We don't have to deal with light pollution or clouds or the atmosphere sort of jostling around. So these are two telescopes, one that's already up in space and one that will soon be up in space. The one on the left you might recognize as the Hubble Space Telescope. It's been going for 30 years now, and it's like really probably the most famous telescope, space telescope of all time. If you've ever seen a gorgeous picture of a galaxy or a nebula, there's a good chance it was taken by the Hubble Space Telescope. And it's a really fantastic telescope that looks in what we call the visible light. So it's the same kind of light that you and I can see in. And it's 2.5 meters wide, so pretty big, but there's sort of like a limit as to how big you can send something up into space, because it's very, very, very expensive to like send something really large and very heavy up into space. Whereas if you're like building something on the ground, then it's easier to build something that's really big. But the Hubble Space Telescope is getting pretty old. So we want to try to replace it, or at least have other telescopes that are bigger and can complement it. And that's where the James Webb Space Telescope comes in. So that is the gorgeous telescope that you can see on the right, gold plated, really beautiful. And it is what we call a segmented telescope. That means that it's not just one big mirror, it's composed of 18 smaller mirror segments. The telescope itself, the mirror, if you take all the little mirror pieces, it's 6.5 meters wide, so nearly 3 times wider than Hubble. And what we're really interested in when we're talking about mirrors is the area, not just the width. So it's like almost like 10 times more effective than the Hubble Space Telescope. And one thing that's really cool and really striking about Webb is that it's coated in gold. And that's because it doesn't look at visible light, it looks at infrared light. So visible light is really good at bouncing off of silver sort of metals like aluminum, which is what we use to coat the telescopes like Hubble that look in visible light. But gold is even better to bounce off infrared light. So we coated all the mirror segments for Webb in gold. So it makes it like really, really unique looking. And where I work, the Institute for Research on Exoplanets, we have a really big interest in Webb, and we have a big contribution in Webb specifically for one mission, which is searching for new worlds or exoplanets. So it's an institute at the University of Montreal, lots of different people, students all the way to professors who are working towards looking for new worlds and searching for life. And when I say searching for life, I mean searching for extraterrestrial life. So that's beyond the Earth. That's like really cool, and you might think something of science fiction, but it's actually going to be in the realm of what we can do in the next 10 or 15 years. So it's super exciting. So what's an exoplanet? So if we start off with something we're more familiar with, our solar system, we have the sun, which is our star at the center, and we have 8 planets that we know about. But the sun is a star like any other star. And for the longest time, scientists and philosophers and astronomers have looked at our sky and seen these other stars. And a long time ago, like 500 years ago, some people started saying, well, wait a minute, we have a star, it's the sun, and we know that there are planets around that star. So maybe all of these other stars that we can see in our night sky also have their own planets or their other worlds. And that's where the concept of an exoplanet came from, the thought of an exoplanet. So exoplanet, if you want to learn a little bit of French here, that's what's written there. Exoplanet is simply just a planet that orbits around a star other than the sun. It's outside of our solar system. Exo is, it means outside. So it's a planet that's outside the solar system. And for a long time, for many hundreds of years, scientists thought of that concept and thought, I bet these things exist. It'd be really cool if we could see them. But it's really, really hard to see these exoplanets because they're sort of lost in the glare of their central star. So think about it. When you're going outside, you can't really see anything that's around the sun because the sun is so bright. There's like a big glare around it. That's why you shouldn't look straight at the sun because it blinds you. So the starlight that is being emitted from these stars just blinds everything that's around them. We have to have really, really special techniques and instruments to be able to detect them. But that started changing about 25 years ago when we developed these techniques and these instruments to observe directly these exoplanets for the first time. So in 1995 was when there was a huge discovery, and an exoplanet was discovered for the first time around a star that wasn't so unlike the sun. So the name of the star was 51 Pegasi. And the way that we discovered this particular exoplanet is pretty unique. So we know that the planets orbit around a star or a sun, but because of the weight or the mass of the planets around them, there's actually a bit of a wobble that happens. There's a movement in the star itself, and astronomers develop instruments that are sensitive enough to look at that sort of little wobble or the little dance that the star is doing because of the mass of its planets. And so this is how we discovered this first exoplanet called 51 Pegasi b. The little b means it's the first exoplanet associated to that star. And this is a very, very strange and unique exoplanet when we first discovered it, because it's nothing like anything that we have in our own solar system. So it's about the mass of Jupiter, about half the size of Jupiter, but it is really, really close to its star. So if you look in the bottom of the slide here, you'll see the orbits or the distance of a few different planets in our solar system with the sun. So you'll have Mercury, Venus, the Earth, and Mars. And you can see just below it how close this exoplanet, 51 Pegasi b, is to its star. It is way closer to its star than Mercury even. So this is the first time we discovered this kind of planet. We call them hot Jupiters. So they're big like Jupiter, but because they're like all pressed up against their star, they get really, really hot. And this is like a brand new kind of planet when we discovered it. We didn't understand how this could even exist because we don't have something like that in our solar system. But as this field of exoplanets went along, we discovered loads and loads of other exoplanets. Some hot Jupiters, but some were smaller, like the Earth. Some were sort of medium sized, like mini Neptunes, or like really big Earths. Some had rings, all kinds of different colors and all kinds of different sizes. And so we realized that there are like lots and lots of exoplanets out there. Right now, we know of more than 4,100 exoplanets. And that's not even that far into the galaxy we've been able to search for them. We've only been able to look really, really close to the sun, because the farther we look, the harder it is to find these exoplanets. But one thing that we're now really interested in doing with these exoplanets that we found is to know a little bit more about them. And the James Webb Space Telescope will be able to give us some really, really cool information about that. So this is a mission that's led by NASA in the US, with very, very big contributions from two partners, the Canadian Space Agency and the European Space Agency. So I work with the CSA, the Canadian Space Agency, on the big contribution that we did, which is like super important. We have a scientific instrument, which I'll talk a little bit about, and we also have what's called a guiding camera. So the space telescope is going to be really, really far out in space. Hubble, if you know a little bit about the history of Hubble, had a little bit of a rough start. When it was launched, there was a problem with its mirror. But luckily, it was launched at what we called low Earth orbit. So it was relatively easy to send up astronauts to fix it. But because the James Webb Space Telescope looks in what we call infrared light, and the Earth glows very brightly in infrared, we couldn't put it in low Earth orbit. Otherwise, there would constantly be this like light pollution coming from the Earth itself. We had to like launch it far away. So it's going to go 1.5 million kilometers away from the Earth. That's really, really far. To give you sort of an idea, the moon is about 400,000 kilometers away. So it's going to be many, many times farther from the Earth than the moon is from the Earth. So it's very, very far away. And it's going to be looking at infrared, as I mentioned. So that's why it's coated in gold. And it's a lot bigger than Hubble. So it's very, very exciting. And when we launch it out there, it's going to constantly be in orbit around something called L2. That's a really fancy name, Lagrange 2, for like a stable point. It's orbiting around the sun, and it's always going to be sort of vibrating a little bit. But imagine if you wanted to take a picture of something really, really far away, and you want to take a nice picture, and you're like constantly vibrating around. You're going to take a pretty bad picture because you're shaking the camera around. So there's something on this telescope called a guiding camera that the Canadian Space Agency and different teams around Canada built, and that will allow the Webb telescope to take really clear and crisp images, even though the telescope is sort of moving around. So it's going to be able to track objects with like a huge amount of precision to be able to take really, really good pictures. This is the scientific instrument that we provided here. And the principal investigator, or the lead scientist that led this work, his name is René Doyon, and he is also the director of the Institute for Research on Exoplanets. So on top, this is about the size of like a washing machine. So it's like big, but it's not, that big. You can sort of imagine it in your living room or in your house. And you have the guiding camera that's on top, and joined on it is something called NIRISS. It's a scientific instrument that does two different things. It takes images like a camera, but it's also what we call a spectrograph. And the spectrograph is something that's super interesting. So you know how if you have the light of the sun, maybe you've seen a diagram, or maybe you've been lucky enough to see like a real demo of this. The light of the sun comes in and you shine it sort of through a prism, like a glass prism, and then you can see all the colors of the rainbow. Even if you haven't seen that like in a demo with a glass prism, you've seen it happen with rainbows, because all of the water droplets around you are acting like prisms when you have raindrops that are sort of turning the light of the sun into that rainbow. So that's what a spectrograph does. It sort of breaks down the light of these faraway objects that we're interested in and shows you all the different individual colors. And when you look at all the different individual colors separated from each other, you get lots and lots more information. So one of the really exciting things that we're hoping to do with the spectrograph is looking at not only the exoplanets that I talked about, but the atmosphere of these exoplanets that I talked about. So I talked about extraterrestrial life before, and that's where we're really interested in finding out. When I say extraterrestrial life, I don't necessarily mean big scary monsters or little green men or anything. For the longest time, the type of life that we had here on Earth was only very, very small and very simple, like bacteria. And so we're looking for that kind of life on these other planets. And one of the things we need to do to find that is to find a world that seems like it is what we call habitable. And that means that it sounds like it's pretty cozy for a life form to develop there. So if something was like really, really hot and there was no liquid water or no oxygen, we couldn't imagine living there. So we would have a hard time imagining any kind of life living there. Of course, we have to base ourselves on our definition of life as we know it here on Earth. There might be forms of life out there that we can't even really understand because they're so weird. So we can only stick to what we know for the moment. So that's what we're looking for. And so we're going to be using this instrument, NIRISS, to look for the atmosphere of these exoplanets and look if they have special molecules like oxygen that we breathe, or water vapor that's very important, or carbon dioxide that we exhale and plants breathe in, or ozone, which protects us from the really harmful rays of the sun, or methane, which is something that almost all life forms emit in the form of flatulence or farts. So that is something that we can look for in these atmospheres to tell us if these planets have the potential for life or have a sign of life that we call a biosignature. So that's one of the really important things that Webb is going to be doing, but there's like lots of different things it's going to be doing beyond exoplanets. One of the things that I'm really interested in, because I like to study galaxies, is that it's going to be studying galaxies all throughout the history of the universe. So the universe is super old. It's almost 14 billion years old. And with the Hubble Space Telescope, we've been able to look relatively far into the universe. So something really cool in astronomy, because light takes a certain amount of time to get from point A to point B, the further you look into space, you're not only looking really far back in distance, you're also looking far back in time. So it's almost like a time machine. So when you're looking really, really far at distant galaxies, you can look at some of the first galaxies ever formed right after the Big Bang. So that's one of the things that James Webb is also hoping to do. So it's going to be able to study galaxies all throughout the history of the universe. And then we could sort of like link up those different informations together and figure out how galaxies evolve over time. So that's another thing that I'm super interested in. There's lots of different things that it's going to be doing, though, things in the solar system, looking at different planets in there, looking at black holes, looking at the life and death of stars. So it's super exciting. We're super excited for it. And it should be launching sometime in the year 2021. So it's going to be a revolution in the world of astronomy. And I, for one, am excited to learn about all of the exciting science it's going to be doing, and also translating that for the general public and making sure everyone is as excited about it as I am.
I'm not sure anyone could be as excited as you are now. No.
Maybe not.
But what a fantastic presentation, and thank you so much. And certainly you've put us on the path to be inspired and excited by all this fantastic stuff. So for anyone tuning in on YouTube, if you guys want to type in questions, please do. Just let me know where you're joining from, and I'll pass as many as I can to Nathalie. But while we're getting started, I want to begin with exoplanets. So we have all these pictures of exoplanets. We've seen them all over the, not solar system, all over the galaxy. Can we ever get to one? Could we end up on an exoplanet? Is that possible?
That's a super good question. And that's often a question that I get because some people say, there's limited resources here on Earth and limited amounts of money to decide where we should put it and what we should study. So why are we putting all this money on these, like studying these exoplanets that are so far away? But the thing is, we don't have any kind of intention to get to these exoplanets. So if I'm talking about the closest exoplanet to us, so we're lucky enough that the closest star to the sun, which is called Proxima Centauri, about 4 light years away from us, it happens to have an exoplanet. It had like a 50% chance of having an exoplanet, but it does. And it's a small rocky planet that might be similar to the Earth. But if I put someone like a human on the fastest rocket ship that we currently have, and it's not even really meant to have someone on it, but like, let's say we could rig it up to have a passenger seat on it, it would still take 7,000 years for that human to get to the closest exoplanet to us. So there's no way currently with our technology that we can get there. But the reason why we still want to study them is because we're interested in finding out more about how the Earth itself was created and how common Earth-like planets are. But because these things evolve over hundreds of millions or billions of years, it's very hard for us to sort of like rewind in our past or look at our future in a super accurate way. So we're trying to study as many exoplanets as possible to statistically figure out how common our type of planet is, or like what our place in the universe is.
Super cool. And so you showed us these exoplanets with all these cool colors, and certainly I've heard stories in the past about, exoplanets made entirely of diamonds. Can we really know what these planets are made of, or is this just something where they're overblowing the science reporting?
So it's a little bit of both. So obviously, if you hear about an exoplanet where it rains diamonds on you, that's like a pretty catchy title for the article. But often scientists can use the data that they get to get a pretty good idea of the type of density that an exoplanet would have. And then you can sort of figure out like what kind of material it could be made out of using models. So we can use the transit method of detection of exoplanets, which is when you have like a star that you're looking at, and then periodically an exoplanet will pass in front of it, sort of like a mini eclipse, block out some of that starlight, and then you can figure out how big the exoplanet is. And then the detection method that I mentioned before, the sort of wobbling effect that happens to the star, that tells you how much mass or how much stuff is in the exoplanet. So if you've looked at what density is, if you have the size of something and the mass of something, you can figure out what the density is. So once you have a certain amount of density, you can sort of rule out, well, is it made of something really dense like a rock? Or is it made up of something not as dense like water vapor? And then sometimes it's a combination of both. So you can sort of figure out with your models what the probabilities are that it's made out of. So they're usually educated guesses, but obviously we haven't been able to send someone there and like look at the diamond planet specifically.
Yeah, but I love this, and I always I can't help suppressing. I can't even suppress a grin with things like this. These places are so far away. As you said, the closest exoplanet would be 7,000 years with our fastest spacecraft. So how sensitive are these detectors able to make out the density of a planet that's that far away or further? Like, what are we talking about here?
So it's really intense how sensitive these telescopes and these instruments are. And probably one of the biggest pieces of evidence that shows how good these astronomers and engineers are is the planets that we've been able to take a direct image of. So I've spoken about ways to sort of see the effect of an exoplanet on its star, either because of the eclipse effect or because of the little wobble that happens in the movement of the star. But For about a dozen or so exoplanets out of the 4,100 that we know of, we've been able to take a real picture of these exoplanets. So obviously it's not like a beautiful picture of a landscape with like an ocean and like continents. It's a bright dot that's next to a brighter dot, which is the star. But if the planet is bright enough itself, so usually that means it's a young planet, which is still emitting lots of heat, and it's far enough from its star that it's not lost in the glare of its star, you can take a picture of it. But taking a picture of that exoplanet next to its star is like asking you to spot a little firefly that is next to a lighthouse from a kilometer away. So it's about 1 billion times fainter. The planet is about 1 billion times fainter, or 100 million times fainter than the star. That's how sensitive these instruments are.
Very cool. All right, we had a question from our group online. So they want to know, how many stars are there? So, we're talking about the whole universe here. What's a way to convey this accurately and in a way that makes sense?
So lots and lots of zeros if I gave the like full answer, and I couldn't even give the full answer because there's lots of the universe that we don't even know about. But if you start off with like one galaxy, one average sized galaxy like our Milky Way, that has about 300 billion stars in it. And in the known universe, we know that there's probably going to be about 1 trillion galaxies. So 300 billion times 1 trillion galaxies equals, lots and lots and lots of stars. And we think probably maybe 50% of those stars have an exoplanet. So when people ask me about, do you think alien life exists? When you count up all the exoplanets that exist, just statistically speaking, it sort of sounds like there's probably alien life somewhere out there, even though we haven't been in contact with it.
I've always loved highlighting for people that if they check out something called the Hubble Ultra Deep Field online, this is a picture of like a really, really tiny bit of sky. Like you hold your arm up to the sky and it's your thumbnail. They show how many galaxies, not stars, but galaxies with hundreds of billions of stars of their own. And that's just the most surreal picture I can think of for that. Fantastic. So that's a really surprising fact. Is there anything really surprising that you discovered in your work personally, Nathalie?
So if I talk about like my own personal research where we start getting really nerdy and then in all the little details and everything, something that I discovered in my PhD thesis is that we found that nature doesn't really like building middle-sized galaxies. It likes making small galaxies and large galaxies, but there's like a little area in the middle where if it tries to make a middle-sized galaxy, it's like unstable and it will quickly try to like gobble up more matter to be bigger, or it will kick stuff out to become smaller. So it likes little things and big things, but it doesn't like middle things.
Fascinating. Very cool. I don't think you've ever mentioned that one of our past talks. That was cool.
Mm-hmm.
All right, we're going to take a few more questions here. So a question we just got online. What do you think the chances are of an advanced society like ours on another planet? Or, do you think there's intelligent life out there?
Intelligent life out there. So that is more complicated than just like life, no matter how simple it is. I really don't know about that one. I think that there's maybe a good chance that there has been intelligent life at some point in the history of the universe, or there will be at some point in the future. But so what do you consider intelligent life? Do you consider an intelligent life form something that can communicate really far away? So that implies that you have to have radio communication or some kind of long distance communication. Humans have had that for 150 years or something. Not very long. So 150 years over the span of 14 billion years is like nothing. It's a fraction of a fraction of a fraction of the history of the universe. And, I don't want to be pessimistic, but humans are not necessarily taking the best care of their planet or everything. So at some point we might stop existing. So the amount of time where we were alive and conscious and able to communicate outwards is going to be a very small fraction of the history of the universe. So maybe something existed 10 billion years ago, And they were like, hey, what's up, everybody, for like a few thousand years while they were like able to, but then they became extinct. And then we just totally missed that. And it just so happens that no other intelligent civilization is existing at the same time as us. And then we'll become extinct. And then someone else, some other intelligent civilization will pop up in like 4 billion years, but they won't have heard our signals. So it's not only a question of space, but it's also a question of timing. Maybe the timing is completely off. And that's why we just haven't been able to talk to anyone else, because we haven't existed at the same time as them.
Yep. Maybe another civilization lives on a star that's 10,000 light years away and they've been broadcasting for 5,000 years, but it doesn't mean this message isn't going to get
reached us
5,000
yet.
years, right? So it's very cool. I always love when we can highlight the scale of time and space. All right, a couple more questions. So David wants to know, do you know how big stars are from looking at them through a telescope? And can you explain maybe how big our sun is compared to some of the bigger stars out there?
Yeah. So I have a pretty good, there's a YouTube video that shows the scale of different things. I don't know if you know the one that I'm talking about, Jesse.
I do, and I'm going to get it in the YouTube chat bar, but you can keep talking about it while I get it.
Perfect. Okay. So one thing that's really hard when we're studying stars with a telescope is that they all look like dots. They all look like the same size of dots. And obviously, something that's really, really big and far away will look the same size as something that's like really, really small and up close. So we have to become really sort of clever to figure out the size of things. And one of the ways that we do that is we use the laws of physics that we know powers stars, the nuclear fusion that happens inside the hearts of stars. And we can figure out the kind of size and mass that they have using those models and using how bright they are and their temperature. So I spoke a little bit about spectroscopy. When you take the light of something and you break it up in all its different colors, you can look at where the peak of the light of a star is. And if the peak of the light of the star is like about in the visible light, like sort of green, yellow light, sort of like our sun, we know it's about 6,000 degrees. And we put that in our models and it tells us it's sort of like an average size star. It's a yellow star. And obviously we use as much information as we can from the sun to power our models because it's the only star that we can like really get lots of close-up information on. But really, really, really hot stars, they will have a peak in like the ultraviolet or even sometimes like the X-ray light. So like they are like really, really hot, like 100,000 degrees hot. And we put that in the models and we know that they're very, 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 very big. They tend to be sort of bluish and white. So we can look at the color that they have and that tells us their temperature, which in turn tells us lots of information about their size and their age and everything. You have red stars, which will peak more like in the infrared and they'll be like 3,000 degrees. So you can like get lots and lots of information on like just the light that you're studying, even though you can't physically see their size. That being said, because we're not only satisfied with that, we're starting to be able to use a technique called interferometry. And that is what we used when we took that picture of the black hole last April. And you're basically using not only one telescope, but a network of telescopes that are talking to each other, acting like one bigger artificial telescope. So when we did that for the black hole last year, it artificially created a telescope that was about the size of the Earth. And the bigger your telescope, the more you have resolution to look at small things. And so we are now able to use that kind of technique, interferometry, now you know a really fancy word, to take better, more high resolution pictures of like really, really big stars like Betelgeuse, which has been in the news recently. It's a really, really big star. And so for stars like that, we can start to see a real picture of the ball, not just like a sort of arbitrary dot that doesn't give you lots of information. So we're getting to the point where we can start taking real pictures of these stars and sort of get real information about their size.
Outstanding, Natalie. Well, that was fantastic. I always want to wrap up with a question. Where can we send kids to learn more about you, about IREX, about James Webb? Where can we push them when they're done this session to keep learning going?
So all the information for IREX is at exoplanets.ca. We also have the website in French, of course. The CSA website is awesome. It has a James Webb Space Telescope section and has a brand new astronomy section, which I'm super excited about. It gives information about stargazing tips. There are fact sheets about black holes and stars and planets, and a bunch of little fact cards about all the different planets in our solar system. So I'm super proud that is up now. I helped work on that, so really excited about that. You can find me on social media, on Twitter at Angry Astro Panda, and I also have a personal website called astropanda.space. And a fantastic website if you want to get into even more detail about the James Webb Space Telescope is webtelescope.org.
Awesome. So I've already linked to a few of those in the YouTube chat bar, and do check them out to everyone watching at home. Thank you so much for tuning in. And Nathalie, thank you so much for joining us again. We really, really appreciate it.
Thanks for having me. Stay safe, everyone.
All right. Have a wonderful rest of your day, and bye for now.